Okay, today we're going to do a little more complicated topic. We're going to talk about the Gaussian integral. And this is an integral that is essential to mathematics, similar to the Dirichlet integral, which was sine x over x. But the Gaussian is even more because of statistics. Statistics, the entirety of the normal distribution curve is based around the area it occupies. And the Gaussian integral is how we computed, or Gauss, like I think he was literally the father of statistics too, but Gauss, the guy who computed the integral, he found the area under the normal distribution curve, and yeah, this integral basically helps you find that area, and that's why it's so useful. What's the integral? Pretty simple. Negative infinity to infinity of e to the negative x squared dx. Yeah, you're probably wondering like what? Okay, well, yeah, you realize there's no elementary solutions to the antiderivative, which means that you cannot integrate this using elementary methods like u substitution, trig sub, yada yada yada. But there is a way that you can use double integrals to solve this thing by hand, and it's a beautiful result. This is actually just equal to the square root of pi. That's it. So where does pi come from? How do you do this? Glad you asked. So let's start. But before we do this, I want to consider the same integral. In fact, let's call this integral I. What integral? Let's consider the same integral, but just slightly different. The integral from negative infinity to infinity of e to the negative y squared dy. Akil, that's the same integral. You just changed from x to y. Yes, but this one is actually, the only difference is this one is based on the area under the y-axis and like this, not like this. But for all purposes, it's the same. Now, I'm gonna do some wonky math that apparently works really well, but you're just gonna have to take like a leap of faith with me on this one. I want to compute, let's say I want to compute I squared. What is that value? Well, I can obviously just multiply this one twice, but that really doesn't do me good. Let's do this. Let's multiply this value and this value because they're both equal to I. And what you'll get is this integral here of e to the negative x squared times e to the negative y squared dx dy. This is, when you multiply, you can basically nest the integral within each other, and you can like work it out like that. Overall, it works because if you integrate this by itself, you'll get I, and I is just a constant, so you can get that out, and you can integrate this by itself. So like, let me explain. This and this. So this is a constant, so this will not change. But if you integrate this by using some magic method that's not known to mankind yet, you'll get I, but then I is a constant, so you can pull that out to the outside, and you'll be left with this, this, and this, right? And that also integrates to I, so that's I squared, because I is on the outside too, so I times I is I squared. This works. Now, let me rewrite this. That's the same thing as the integral from negative infinity to infinity of e to the negative x squared plus y squared dx dy. If you have taken, or if you have done any surface or like area integrals, double integrals in your life, this is the biggest give me known to mankind. This is probably like a layup for you, because why? You have an x squared plus y squared. Polar coordinate substitution. So I'm gonna let x equal to r cosine theta, y equal to r sine theta, and x squared plus y squared equals r squared. Now, if you haven't taken calc 3 before, you kind of have to just take a leap of faith with me when I say dx dy equals r dr d theta, and let's say we want to find what dx dy equals. And what is dx dy? Well, that's small changes in the x direction, small changes in the y direction. So this little box over here, that's dx dy. So if I want to compute this, want to find the area of this little box in spherical coordinates, not spherical, polar coordinates, well, because this is dx dy, well, maybe if I cut this into sectors, right? And I want to find the area of this little box here. That little box, let's just say it's translated up over here. It's the same area, it's just this is moved up over here. So like this is like dx, this is dy, it's just moved up. And since we're talking about the small values, it's the same thing. Well, I want to figure out what the length of this is and the length of this is. When you're doing sector length, it's r times the angle. And the angle is d theta. And the radius is just the radius, so that's r d theta. And this is the slight change in the radius, this is dr. So if you multiply, you get dx dy equals r dr d theta. So that works. So let's substitute now. E to the negative r squared, r dr d theta. Okay, but what values are we looking for? Keep in mind, we're integrating a surface, and obviously this value is going all the way to infinity, and that's going to be all the way that way, 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 because we're doing x's and y's. Radius is going to be infinity at the maximum, right? It's going to be from 0, right? Because we're going to be at a very small point, like over here, like at the origin. And then we're going to go all the way to the infinite sides. So, to infinity. And since we're talking about the radius in that way, that way, that way, and that way, we're going to integrate the angle from 0 to 2 pi. Okay, well, this is pretty easy now. You can kind of really see that no matter what value you get over here, like this value is some constant k, you can essentially, like, since there is no thetas over here, this will basically be this. So let's say that this value over here is k. So if you integrate k with respect to theta, and theta doesn't exist, right, it's just a constant k, it's really just you're gonna get k theta. Integrate from 2 pi to 0, you plug in 2 pi, you subtract the value that you plug in 0, you just get 2 pi. So let's just bring a 2 pi to the outside, times the constant, which is really just the integral from 0 to infinity of e of r times e to the negative r squared dr. Right? That's where we get the 2 pi from. Well, this is a gimme. This is a gimme in u substitution. So we're going to let u equal negative r squared, du equals negative 2r dr. This 2 is right here. Obviously, no negative. Let's multiply by -1 and also divide by -1. Yeah, so then this will go that way. So we're going to have a negative pi because the negative is absorbed by the du. Our bounds are going to be a little different. So let me move this over here. This equals negative pi times the integral. All right, our bounds is going to be different. So when we plug in a 0, we're gonna keep a 0. Yeah, when we plug in a 0, we're gonna keep a 0. When we plug in infinity, negative infinity squared is infinity. No, infinity squared is infinity. Times negative is negative infinity. Times e to the u du. Now you can take this negative and switch the order. So this is pi times negative infinity to 0 of e to the u du. Well, we can integrate this now. This is equal to pi times e to the u plug in from negative infinity to 0. Now we're going to take a limit, but I'm going to skip that notation. E to the negative 0, e to the negative infinity is 0, e to the 0 is 1. So we're going to have 1 minus 0, that's just 1. So pi times 1 is pi. Now keep in mind, let's move this over here. Final stretch. This is all equal to I squared. So I squared equals pi, and we're trying to find I. So ladies and gentlemen, square root both sides. This area is going to be positive because it's only above the xy plane in the 3D sense. But trust me, it's just positive. So I is actually just the square root of pi. And that's the Gaussian integral.